In this lesson, you'll learn about propellers, their function and operation. Although we will, of necessity, very occasionally make mention of the aerodynamics of propellers, it is important you be aware that this is not a lesson on the aerodynamics of propellers. Propeller aerodynamics are dealt with in the subject Principles of Flight. The purpose of a propeller is to provide thrust to drive the aircraft forwards through the air. This is achieved by accelerating a comparatively large mass of air rearwards, thereby producing forward thrust. A propeller consists of two or more aerodynamically shaped blades attached to a central hub. This hub is mounted onto a propeller shaft which is driven, either directly or indirectly, by the engine. The hub and the blades are thus spun round by the propeller shaft, and act rather like wings, which by rotating would generate lift, or in this case, thrust. In order to be able to explain how a propeller works, it's necessary that we use a certain amount of terminology. Like a wing, a propeller blade has a root and a tip, a leading and trailing edge, and a cambered cross-section, whose chord line passes from the center of the leading edge radius to the trailing edge. The cambered side of the blade is called the back, while the undercambered side is termed the thrust face. Where the section of the blade becomes round at the root area is termed the blade shank, while the base of the blade is called the blade butt. The propeller blade is set into its hub so that its chord line forms an angle with the plane of rotation of the whole propeller. This is called either the pitch or blade angle. The theoretical distance, ignoring slippage, that a propeller or propeller blade moves forwards when the propeller shaft has completed one rotation is called the geometric pitch. All propellers, however, lose a certain amount of efficiency due to aerodynamic and compressibility losses. As a result, the geometric pitch can never be achieved. The actual distance that the propeller moves forward during one revolution is called the effective pitch. The efficiency loss, that is, the difference between geometric pitch and effective pitch, is known as slip. The efficiency achieved will usually be in the range of 80 to 90%, and can be found by using this formula. The path of the propeller blade through the air, which describes a helix, determines the direction from which it will receive its relative airflow. This helical path is the resultant of the propeller blade rotational velocity and the aircraft forward velocity. The angle between the relative airflow, the actual path the blade describes through the air, and the chord line of the blade is called the angle of attack. The angle of attack is kept quite small, usually between 2 to 4 degrees. As the blade rotates at this small, positive angle of attack, a thrust force is generated, very similar to the way in which lift is generated on a wing. Because the rotational velocity of any point on a propeller blade increases with increasing distance from the center of the hub, so the magnitude of the thrust generated at any point along the blade would also increase with this distance, if the pitch of the blade remained constant along its entire length. If the blade pitch remained constant along the length of the propeller blade, the increase in force developed by the outer part of the blade, compared with that developed at the slower-moving blade root, would tend to bend the blade as depicted here. The angle of attack depends on blade angle, the rotational speed of the propeller, and the forward speed of the aircraft. To keep the angle of attack within necessary limits along the length of the blade, we therefore reduce the blade pitch from root to tip. This has the effect, when the aircraft is in flight, with the propeller rotating at its designed operating RPM, of maintaining a fairly constant thrust force along the length of the blade. We've just seen that a propeller receives its relative airflow from a direction which is governed by the aircraft's true airspeed in the direction of flight, and its own rotational velocity in the plane of rotation. The operating angle of attack will be the angle between the relative airflow and the chord line of the propeller blade. This chord line is set at an angle to the plane of rotation, which, as we've already seen, forms the blade angle or the propeller pitch. From this animation, it can be seen that an increase in true airspeed will reduce the angle of attack, whereas an increase in rotational velocity, or RPM, will increase it. At high true airspeed and low propeller RPM, for instance with the aircraft in a power-off dive, it's possible to reduce the angle of attack to 0. While at low true airspeed and high RPM, for instance in the climb, it's possible to stall the propeller blade. Both extremes are obviously inefficient and therefore undesirable. The conclusion that must be drawn is that for a given fixed pitch, a propeller will only work efficiently at one combination of true airspeed and RPM, as is shown in this diagram. The propeller designer will attempt to ensure that peak efficiency is achieved at cruise true airspeed and cruise RPM. When a fixed-pitch propeller is being driven by a piston engine, the RPM is dependent on both the power setting, throttle position, selected by the pilot, and the true airspeed of the aircraft. It would be possible to overspeed the engine in a dive if the throttle was not closed. Conversely, with the aircraft stationary on the ground, it may not be possible to achieve rated RPM with the throttle fully open. Because of all of the disadvantages of the fixed-pitch propeller that we have just mentioned, advanced piston engine aircraft are fitted with variable pitch, constant speed propellers. This type of propeller is able to operate efficiently over a wide range of airspeeds. The power setting of a piston engine is defined by a combination of manifold pressure and engine RPM. Where both a separate power lever and a propeller RPM control are provided, it's possible to vary one of these parameters while leaving the other to remain constant, so optimizing the operation of the engine-propeller combination to give the best efficiency and fuel economy, while reducing the engine wear and tear to a minimum. In order to achieve this, a variable pitch propeller is used. The system changes the pitch angle of the propeller blade to vary the load on the engine, thereby maintaining the selected RPM of the engine-propeller combination independent of manifold pressure, provided that the propeller is operating between its fine and coarse pitch stops. The fine and coarse pitch stops may be fitted internally or externally, depending on the make of the propeller. Once an RPM has been selected, a control unit, either a constant speed unit or propeller control unit, will automatically vary the propeller blade pitch angle, and therefore its angle of attack to the prevailing relative airflow, in order to maintain the selected RPM despite variations in airspeed and manifold pressure. Variable pitch propellers may also have a reverse pitch and/or feathering function, the advantages of which will be discussed later in this lesson. This animation shows that under normal propeller control conditions, it's possible to provide a range of propeller pitch angles ranging from max course, cruise, all the way through to reverse pitch. The alpha, or constant speed range, is used for normal flight. It includes all pitch angles from flight fine through to max course, while the beta, or ground range, includes pitch angles between flight fine and maximum reverse. The feather position is not included in either range, and is used for emergency conditions only. In the event of engine failure, the propeller blades will be moved directly to this position to prevent windmilling. There are no pitch angles available between max course and feather. The method of control within the alpha and beta ranges, and the means of achieving the propeller feather position, will be discussed progressively throughout this lesson.